to our Channel of Sciences and Mathematics. Our topic for discussion today is the concept under volumetric analysis, and that is going to be the concept of back titration. Now, sometimes when we are doing a chemical reaction, you find that the reactant is slow to go into conclusion. So basically, in this case, it requires us to add the reagent in excess so that we can be able to assist this particular chemical reaction to go into conclusion at maybe a convenient time. So this pertains to the concept of back titration, and we're going to see, using the questions that are posted on the board, how we can be able to go around questions that relate to the concept of back titration. So without further ado, thank you and welcome. So our discussion for today, as I've said, is a concept in volumetric analysis, and we're going to revisit a few of the discussions that we have had on the topic of titration, and that's basically what the requirements for titration to be successful. So the first one we mentioned under the discussion about the titration was that this reaction should be stoichiometric. And number two, we said that it should be rapid enough. And then we said that the reaction must be complete. So this case means that it has to have an endpoint. So therefore, and then we said that it should have a convenient way of detecting the endpoint. Convenient way of detecting the endpoint. And lastly, we said that it should have minimal side reactions. So therefore, for an analysis that pertains to the concept of titration, these are some of the conditions that it requires for the process to be achieved successfully. So therefore, we also talked about the concept of requirements for a primary standard, which we have said, of course, in our discussion under the concept of titration, of course, an introduction to titration. And we said that for a primary standard is a solution that is prepared by dissolving accurately weighed quantity of highly pure material. And therefore, we said that the requirement for this primary standard is that it should be 100% pure, or maybe as an error margin of this is plus or minus 0.001%. And number two, it should be stable at room temperature. Stable at room temperature. So therefore, these are the requirements for a primary standard, whereas these are the requirements for the process of titration to be achieved successfully. So having mentioned that, in my introduction, I said that sometimes the reactant is slow to go into conclusion, and this difficulty, therefore, to get an endpoint. So therefore, this requires us to maybe know the amount of reagent that is added to the analyte solution, which of course is done in excess to facilitate, of course, completion of this specific reaction that we have talked about. Now that we have mentioned that one of the conditions for titration to be successful is that it should have a convenient way of detecting the endpoint, and number two is that it should, of course, it must be complete. So therefore, in order to achieve this, the process of back titration is performed, or the procedure for back titration is performed, whereby a portion of the reagent react to the analyte, and the excess can be determined by titrating with another standard solution, of course, which we say is a solution whose concentration is unknown. Now, the amount of analyte is determined by the difference that is found between the reaction that we have said of excess reagent with the analyte solution, and the different reaction stoichiometries are therefore used in order to determine either the mass or the number of moles of the reacting substances. Now, the relationship that is used between these is that the moles of the titrant reacted, maybe you can use the term reacted, is equivalent to the moles taken subtracted by the moles back titrated. So this one will make sense when we are trying to, of course, try to solve this kind of reaction, and therefore we can find the amount of analyte, or perhaps using the stoichiometric relationship or the concentration that we had, of course, discussed using some of these concepts that we have already talked about, whereby the concentration maybe in molarity can be found by this is grams per liter divided by the relative formula mass of the compound that is used. Now in this case, of course, we'll have to use the question that we have posted on the board in order to understand in details how we can be able to perform this concept of back titration. So therefore I'm going to go through the question, and from there we can be able to try and see how we can be able to find a solution to the challenge. So 0.47 grams of a sample containing sodium carbonate was titrated with a 50 ml 0.1 molar HCl. Excess HCl was back titrated using 0.1 molar standard sodium hydroxide, where 20 ml of sodium hydroxide were used. Calculate the amount of sodium carbonate in the sample. So in this case, it's good for us to find a stepwise way in which these reactions are taking place. I'll try to find a convenient point at which we can be able to develop a relationship between these reactants and the product. So therefore, I'm going to just have a look at this information that we are going to extract from there. So this is 0.747 grams of a sample, 47 grams of a sample that is containing sodium carbonate. So therefore, this is part of sodium carbonate is part of this sample. Was titrated with a 50 ml. So was titrated with 50 ml 0.1 molar HCl. So in this case, we are going to see that there is a relationship that is being developed from this particular point, whereby we are finding 50 ml of 0.1 molar HCl was being used. So therefore, from this relationship, we can be able to find the number of moles of the acid that were used in this specific instance. But maybe it has not given us the exact ratio between the acid that was used together with the carbonate. So this is in totality the number of moles of the acid used. So basically we can find the total number of moles of acid in 50 ml. So we can use the relationship and say if 0.1 moles are contained in 1,000 centimeter cubed of HCl, so what about 50 centimeter cubed? So we drew a cross relationship to find x number of moles. So x moles will be given as 0.1 moles times 50 centimeter cubed. I'm just deliberately using, of course we are just trying to find the number of moles, but I'm deliberately trying to use these units in order to see, for us to see how we can be able to come with the units which are required. So about 30 centimeter cube. So you can see the centimeter cubes go out. So therefore, this is just basically going to give us the number of moles that we require, which were used, or maybe of the acids present initially, which is going to be 0.005 moles of acid initially present. So from this, therefore, we are going to look at the second part of the equation and what it says. So excess HCl was back titrated using 0. This one, of course, I can just do away with it because of space. Excess HCl was back titrated using 0.1 molar standard sodium hydroxide, where 20 ml of sodium hydroxide were used. So this also is a second part of information that we are being given. So therefore, this is an acid-base reaction whereby we are going to have a stoichiometric equation for sodium hydroxide plus HCl to form sodium chloride plus So of course a neutralization reaction, so therefore it's going to form sodium chloride plus water. So an acid-base reaction, neutralization forms a salt plus water. So if you try to look at this, so it is balancing it, so it's a stoichiometric equation as a requirement for titration. So the reacting mole ratio is going to be 1 to 1, that is for the base to acid, 1 to 1. So therefore, having been told that was titrated using a 0.1 standard, so the concentration for this one is known, 0.1, where 20 ml was used. So for 20 ml, so we can just use the relationship and say 0.1 moles of sodium hydroxide contained, or maybe contained in 1,000 centimeter cubed. What about 20 centimeter cubed? A centimeter cubed is equivalent to an ml. 1 ml equals 1 centimeter cubed. So therefore this relationship still holds. So we will have 0.1 times 20 divided by 1,000, which is going to give us maybe x2 in terms of moles. So this is basically going to give us 0.002 moles sodium hydroxide. Of course, since the mole ratio for this is 1:1. So if you try to look at the relationship between these two, the first one is an acid reacting with a carbonate, whereby the initial number of moles of the acid were this 0.005. But the second reaction, whereby the excess acid is reacting with a base to form maybe salt plus water, the mole ratio is 1 to 1. Therefore, the number of moles of acid that is reacting is equivalent to the number of moles of the sodium hydroxide. We can see from these particular two reactions that the number of acids that were initially present and the ones that were used in order for the reaction to go to completion were 0.2. Therefore, the difference between this initial and the last ones were used will give us the number of moles of the acid that reacted with the carbonate. So therefore, we're going to find the difference between those reacting mole ratios, whereby the initial number of moles of acid present were 0.005 moles, but after back titration, 0.002 moles of acids were used. So therefore, initially, so this is the number of moles of acid that reacted with a carbonate. You can just write to that one, but remember, it's just a radical. But remember that this is just this one I'm just going to write it in short to represent the sodium carbonate. So therefore, the difference between the two is going to give us the stoichiometric relationship between the number of moles of acid and the carbonate that was used. So this is going to be achieved using an equation whereby we are going to have a sodium carbonate reacting with the acid. So basically this will form a sodium chloride plus CO2 plus of course water. So we'll see whether that equation balances. There are two sodiums here, so introduce a 2 there. And for chlorine, we are going to have a 2 at this specific point. So therefore, that equation balances. But our main concept, our main point of interest is the mole ratios for reacting between the acid and the carbonate. So this is the carbonate and the acid. So we want to find out what amount of acid or the carbonate that reacted. So having seen that the difference between the final amount of moles that were used by the acid and the initial ones that were present gives us the moles of the acid that reacted with the carbonate. So therefore, we're going to find the mole ratio between the acids and the carbonate in order to find the number of moles of the carbonates that were used. So therefore, if the number of moles of this particular acid that were used is 0.003, therefore for this one it's 0.003 divided by 2, 0.0015 moles, of course, moles of the carbonate that was used. These are the number of moles of the carbonate that reacted from this relationship between the mole ratios. Therefore, having seen that, I mentioned that the concept of a relative formula mass. Having found the number of moles that reacted, we said that a mole for compounds is the total number of masses of the constituent elements that make up that compound, which referred to the relative formula mass. Therefore, we're going to find the relative formula mass for sodium carbonate, which is going to represent 1 mole of that specific compound. So the relative formula mass of our sodium carbonate, this is for sodium, we have 2 into 23. I'm correct for that. Okay. So plus carbon is 12 times 1. So therefore plus oxygen is 3 by 16, which is 48. So this is 46 plus 12 plus 68. No, that's going to be 48, not 68. So this is plus 48. So this is going to give us a total of 106 grams. So therefore, the relative formula mass for sodium carbonate is 106. And this basically 1 mole is going to be equivalent to 106 grams. So we're going to make this comparison between this and the number of moles of the carbonate used in order for us to find the amount of sodium carbonate in this specific sample. So I'm going to do away with this. So therefore, we'll use the relationship 1 mole of our sodium carbonate is equivalent to 106 grams, which is a relative formula mass, at about 0.0015 moles. Will give us the amount in grams of the carbonate in that sample. So 0.0015 times 106 divided by 1. This is going to give us 0.159 grams. So this is the amount in mass of the carbonate that was obtained in the sample. Now from this, of course, we can be able to calculate the percentage mass of that specific compound of sodium chloride in the sample, sodium carbonate in the sample, and etc. So in this case, we have used the stoichiometric relationship between the acid-base reaction and the acid-carbonate reaction in order to find the number of the mass of carbonate that was initially in the sample. Now this relationship we're using excess of course, what we call the analyte, or the amount of the reagent that was added to the analyte solution in excess, which is of course was the acid, the HCl, can be able to assist us work with the similar questions that are relating to that concept of back titration. So we're going to see many of the examples in the volumetric analysis that are going to take this approach, but I hope that this one example that we have discussed is going to lay a basis for us in understanding the concept of back titration. So I hope that we have got maybe been able to get one concept or two which we can be able to use and trying to solve similar problems. So that is it for today, guys. Bye. God bless.